Today we're going to finally talk about the situation where we have a second order linear homogeneous differential equation with constant coefficients in the case where the characteristic equation has repeated roots. So remember, if we have this second order linear constant coefficient differential equation, ay double prime plus by prime plus cy equals 0, the characteristic equation is ar squared plus br plus c equals 0. And we've already seen the conditions for when this equation has exactly one real solution. Here a, b, and c are real, so it would have to be a real solution. And the conditions for when it has two real solutions or two non-real complex conjugate solutions. So there will be one repeated root of the quadratic polynomial on the left when b squared minus 4ac, that's the discriminant, is 0. And in that case, that root we're going to call r naught will be exactly minus b over 2a. That just comes directly from the quadratic formula, and you can plug it in and check that. Now, in that situation, we can take the quadratic ar squared plus br plus c, factor out the a, and then, oops, I put that in the wrong place. You have r minus r naught quantity squared, which, so you have the one root, so one linear factor there, repeated, so it'll be squared to give you your quadratic. The a there is to match the lead coefficient, and we can write that as a times r, should be r squared, minus 2 r naught r plus r naught squared. That's how we can write this characteristic polynomial in this case, in this special case. Now, we already know one solution to this differential equation. That one solution is exactly y1 is e to the r naught t, where r naught is that one solution to the characteristic equation. So that's y1 equals e to the minus b over 2a times t. So we know that is a solution. But we also know that in general we have two independent solutions that form a fundamental set of solutions. And here we've got only one. Of course, every multiple of this solution is again a solution, but you're not going to get a second independent solution just by taking multiples of this one. So how do we find it? The following is a very common technique to find the general solution. Once we know a single solution, y1 of t, we ask, how can we find the general solution as some function of t times that one solution? You'll note that if this function of t were just constant, we would just have our one solution to begin with. But if we get non-constant things here for the function v of t, then we'll have other solutions. And we know that already that we should expect to have one more independent solution. Now, this is kind of the technique that generally goes by the name variation of parameters. And we'll see how we can use this variation of parameters technique in more generality later. Here, we're calling it reduction of order because when we use this variation of parameters technique to try to find this v, we'll see that we actually can get a differential equation that v must be a solution to, and that differential equation will be one where we can actually solve it easily by reducing the order of the differential equation. Let's see how that works. If y is v times y1, then we can just differentiate and find y prime is v prime times y1 plus v times y1 prime. That's just using the product rule to differentiate. And then we compute y double prime again by using the product rule twice on y prime, and we get y double prime is v double prime y1 plus v prime y1 prime plus v prime y1 prime again plus v y1 double prime. And of course you can write this as v double prime y1 plus 2v prime y1 prime plus v y double prime y1 double prime. So the question is, what functions v will then allow us to get a solution y here of this form to be a solution to the differential equation y double prime. This is a y double prime plus b y prime plus c y equals 0. I've divided through by a and we get this, and let me write down what happens when we plug that in here. Y double prime is just what we have here at the end. That's v double prime y1 plus 2v prime y1 prime plus vy1 double prime, and then we're going to add b over a times y prime. Y prime is just v prime y1 plus v y1 prime, and then we're going to add c over a times y. C over a times y, that's c over a times y is just v y1 prime. Now, what are we going to do? We know that y1 is a solution to the original equation. In other words, y1, when we plug it in here on the left, this equation holds. So if we look at this, the terms that I circle here, this term plus the b over a times this term plus c over a times this term, in other words, this whole term here, these circled terms amount to just the function v times exactly times y1 double prime plus b over a y1 prime plus c over a y1. y1, this should be just y1, not y1 prime. And so the sum of those circled terms is exactly 0. And what I have left is v double prime y1 plus 2v prime y1 prime plus b over a v prime y1. And if I put in what y1 is, remember y1 is given up here. Let me compute this here. y1 prime will be exactly minus b over 2a times e to the minus b over 2a times t, and y1 double prime, we won't need that, so I'm not going to compute that. We'll plug that in here. We get v double prime times y1, which is e to the minus b over 2a times t, plus 2v prime y1 prime, so I'll write that as v prime times 2y1 prime, which is 2 times this thing, which is exactly a minus b over a, oops, let me fix this. It's going to be minus b over a times e to the minus b over 2a times t, plus I have b over a times v prime times y1, which is e to the minus b over 2a times t. You'll notice these cancel, and I get exactly v double prime times e to the minus b over 2a times t. Well, this will equal 0 exactly when this equals 0. And since e to the minus b over 2a is never 0, e to the minus b over 2a times t is never 0, I can divide through by that, and I need v double prime must equal 0 in order for this equation to hold. So once you know v double prime is 0, this is why we call it a reduction of order. This is, of course, a second-order differential equation, but it's really a first-order differential equation for v prime, saying v prime has to be 0, and then the derivative of that has to be 0. You can easily just go through the two-step process or recognize immediately the solution there is that v of t must be just some linear polynomial, one constant times t plus a second constant. And thus, our solution y of t, which is v of t y1 of t, that has to be a function c1t plus c2 times e to the minus b over 2a times t. Let me rewrite it in this way. C1 t e to the minus b over 2a t plus c2 times e to the minus b over 2a times t. We've actually found the full general solution now because we found the full general solution for the v's that will work in this situation. And you'll notice the general solution is exactly what we would get if we knew one solution. This is what we've already called y1, which is e to the minus b over 2at. And we knew a second solution, I'll call this one y2, just t times e to the minus b over 2a times t. Y of t must be the linear combination of y1 and y2. It's also easy to check, and I'll leave this to you guys to check at home, and please do it. The Wronskian of y1 and y2, where these are the functions y1 and y2, is never 0. So that in fact, these solutions y1 and y2 are a fundamental set of solutions. And as we already have seen, y of t, which is the general linear combination of y1 and y2, is in fact the general solution to the differential equation.